Okay, now let's consider the solvent optimization for a good separation, but in this case with two or three organic solvents. We have seen how to optimize one solvent and aqueous buffer optimization. Okay, change the ratio between um, organic solvent and aqueous buffer, and then we can run HPLC and see which combination, which ratio gives you the best result. Okay, in that case, we our first choice of solvent is acetonitrile, and then methanol, and then what? Tetrahydrofuran. Okay, and likewise, the optimization with two or three organic solvents. So the first choice of course, is acetonitrile. Okay, let's look at this triangle. Okay, at each, you see this apex, and acetonitrile and methanol and THF, and between A and B, the D is the combination of acetonitrile and methanol, and this line F is the combination of methanol and THF. Okay, and then E, between the A and C, is the combination of acetonitrile and tetrahydrofuran. Of course, in all these cases, we mix these solvents, okay, with aqueous buffer. Okay, and of course here the middle is the G. G is the combinations of all three solvents and water. Okay, and let's examine how to do it. We simply follow the steps. All right. The first step is optimize the separation with acetonitrile and buffer to generate chromatogram A. Okay, here is the chromatogram. Look at that. This chromatogram, by the way, there are seven uh, the organic molecules. So you want separate these, the species very well, using the combination of the organic solvent. Okay, you have to decide what solvent or what solvent you are going to use. Okay, so the first one is the acetonitrile and water, the aqueous buffer mixture. Okay, and this is just like one solvent optimization. So, and by changing the volume percent of acetonitrile, okay, you have to try several mixing ratio, and then here the best one was given by 30% acetonitrile and 70 volume percent buffer. Okay, and look at this chromatogram, and 1, 2, 3, they are well separated, and 6 and 7, these compounds also are well separated, but problem is 4 and 5. Okay, this one, meta dinitrobenzene and para dinitrobenzene is not well separated. Okay, so um, they are choosing acetonitrile, whatever the ratio is not adequate solvent. Okay, and then we move to the B, the B. Okay, here uh, the second step is optimize the separation with methanol and buffer to generate chromatogram B. Okay, here, yeah, we do the same, you know, the trial as in acetonitrile. Okay, then you may find that 40% methanol and 60% aqueous buffer may be the best, but you don't have to do the for example, the 10% methanol, 20%, 30%, and like that. That makes the number of trials too many. Okay, yeah, here is a good guide. Okay, you see. take a look at this nomogram. Yeah, nomogram shows volume percentage of the solvents having the same eluent strength. Okay, look at that. Here is the acetonitrile and the purple, the mixture, and then this scale shows the eluent strength. Okay, the volume, uh, the the numbers means the volume percent of solvent. Okay, for example, here 20% means acetonitrile takes 20% by volume. Okay, and 80% is taken by water. Okay, and likewise. Okay, and methanol and water mixture, the scale is like that. All right, and but the distance between this what the numbers are here the different. Okay, and also same way the tetrahydropurane and water mixture. Okay, and this is a nomogram, and you draw the vertical line. Vertical line means that in the same eluent strength. For example, for the acetonitrile and water mixture, let's say you draw the line here, and 30% acetonitrile has the same eluent strength with methanol and water mixture, which is about 40% methanol. Okay, and this eluent strength is here for the tetrahydropurane and water about 22% tetrahydropurane. They gives the same eluent strength. Okay? So the first thing you have to do is that in this case, to obtain chromatogram B, you make uh, the same eluent strength. Okay, here from A, yeah, chromatogram A, we learn that 30% acetonitrile here uh, and water mixture has the same eluent strength of methanol and water, at which methanol percentage is about 40%. Okay, so here when you try the solvent B, you start with methanol, and make its volume percent is 40. Okay, to make the same eluent strength as in chromatogram A. Okay, you understand, and then you get this chromatogram, and then look at this chromatogram, and 1 and 2 is not well separated. Okay, already the methanol and aqueous vapor, it's not a good combination. Okay, and 5, 6, and 4, they are also not well separated. Okay, and then move to C. Okay, the C is the THF. Use THF. This is a single organic component, and then what percentage of THF? Okay, okay, looking this nomogram again. Uh, Actually, THF to make the same eluent strength, and then the THF percentage is about 22. Okay, but here actually trying 22 THF and 78% aqueous vapor gave the worse chromatogram than this one. So in that case, you change the ratio, and then the 32% THF and 68% aqueous vapor gives you this chromatogram. Oh, this is actually quite good. Okay, because compounds 1, 2, 3, 4, 5, 6, 7, okay, are well separated. All right, but don't stop here. Okay, and then we now we tried only one organic solvent, but now let's try two organic solvents and aqueous vapor mixture. Okay, and then now what to try? A combination of A and B, of course with aqueous vapor, and then 15% acetonitrile and 20% methanol and 65% vapor. Okay, gives you this chromatogram. Okay, how do we do that? Well, here since aqueous buffer is common, right? So here, if you add these two, the solvents, and then since you added, for example, by equal amount, and then as the nitrile is diluted, yeah, its a volume percent became the half of it. Okay, so 15%, and then methanol also, volume percent became half, is 20%. Okay, but water uh, buffer doesn't volume percent doesn't change much. Okay, so let's try this two organic solvents uh, and buffer, aqueous buffer mixture, okay, as a solvent. Okay, and then we get this chromatogram, and unfortunately this chromatogram is also not very good. Why? Because compound 4 and 5 are not well separated. Okay, and then so we reject this combination, and then we go for the combination of methanol and tetrahydropurane. All right, and then we get this one. Okay? This uh, F. Oh, we missed E. Okay, F chromatogram, right? With 20% methanol and 16% THF and 64% buffer. Why? Why this ratio? Because we simply assume that you mix the equal volume so of B and C, okay, and then 40% methanol becomes half, okay, 20% here now, and then 32% THF, no, it's a volume becomes half, so 16%, right? And then we get this one. And I like this one the most. Okay, I like this chromatogram C. Well, actually, I like F the most. So I draw this red this rectangle. Okay, uh, compound 1, 2, 3, 4, 5, 6, 7. All these compounds are well separated. You may like the chromatogram C. Well, yeah, it's up to you. Okay? And then let's keep going. Now it's the combination is what? A and C. Okay, let's mix them together. Okay? And then the acetonitrile became half, so 15%, and tetrahydrofuran and became half, 16%, and the rest is aqueous buffer, and you get this one. Wow, this is very bad because compounds 4, 5, and 6 are not separated. Okay, and this is rejected. And then as a final combination, let's all mix up, all mix the solvent A, B, and C, and then what? We mix them together. Mm, and then this one as a natural percentage became 1/3. Yeah, so 10%, and methanol became about 1/3, is 13%, and THF also became 1/3, it's approximately 11%, and the rest is aqueous buffer, and we get this chromatogram. Still, this is not good because compounds 4 and 7 are not separated at all. Okay, so from this kind of trial, so we followed. Okay, we followed the step from step 1 to step 6. Okay, and then successfully we came to know that the combination of B and C and water, okay, it gives you more or less the best result. Okay, okay, I like this one the most. Okay. So if all these trials are not working very well, and then maybe you have to try different um, what different stationary phase. Okay, for most cases, and then if you closely follow these steps, and then you will get the optimum uh, what the solvent combination. Okay. All right. So now you understand how to use this nomogram. Yeah. Okay, after optimize the solvent still need to improve resolution. Yeah, to increase the resolution, yeah, you can decrease flow rate. Okay? If you decrease flow rate, and then you will have a better resolution, and increase column length, of course. Yeah, longer column length gives you more chance to separate the species, and decrease particle size. All right. Yeah, these these things you can try. Okay, okay let's temporarily stop here.